Welcome to Center of Math's Images in Math. Today we're going to talk a little bit about platonic solids. So platonic solids, they're just three-dimensional shapes where each of their faces is regular, and around each vertex you have the same number of faces. So the regular figures, they're just polygons with each angle and each side are equal to each other. So like triangle, square, pentagon, hexagon. And we built the platonic solids from these regular polygons by surrounding each vertex with the same number of such polygons. So we're going to explain why there are only 5 possible platonic solids, and we're going to show what they are. So first, note, given some regular polygon, so same number, same length, size, same angle, each angle. So this polygon, draw a point in the center of it, draw lines to each vertex. Now, note we can break this up into, say this has p sides, we can break it into p triangles. So each triangle has a sum of 180 degrees of its angles. So adding up the angles of all these triangles, we get p times pi is the amount of degrees we have. And then subtract off the angles inside here, which all sum up to 2 pi because it's one revolution. We have the total sum of all the angles in this polygon is p times pi minus 2 pi. And then each angle is the same, so we divide by p to get the measure of each angle. So it's 1 minus 2 over pi, 2 over p times pi is the measure of each angle. So note, in our platonic solid, imagine around a vertex, you took each of the polygons and kind of rose them up so they're all on the same plane. And note that we should be able to do this because you raise them up, they should really just the edges should get farther away from each other as opposed to closer. So this gives us an inequality that q, which is the number of polygons we have around each vertex, times theta, which is the angle of each angle in each regular polygon, should be less than 2 pi. So using this inequality, we can show there can only be 5 possible polygons. So note that if we have, so we get this inequality, 1/2 is less than 1 over p plus 1 over q. Note that if p equals 6, we get 1/3 is less than 1 over p, or yeah. If q equals 6, we get that from this we'll get p must be less, p must be less than 3, but this is impossible since each polygon must have at least 3 sides. And same, if we said p equals to 6, we get q is less than 3. Also impossible, we should have at least 3 polygons around each vertex. So p comma q must both be less than or equal to 5. So this gives us only a finite number of cases to check whether or not a polygon exists. And we can check that from this we're going to get 5 different platonic solids. So yeah, you check all the possible cases. If one of these equals 1/4, then the other one must be less than, or the other one must be less than 4, so only use a possibility of 3. So we have 4, 3. If one of these is equal to 3, the other one must be clearly less than 5. We have 3 cases here, 3, 4, 5. So yeah, when one equals 4, the first one equals 4, we also have a possibility of 3, and when the first equals 5, we also have a possibility of 3. So this is, we have 3 different shapes that each have triangles as their regular polygons, one that has a square and one that has a pentagon as a regular face. And we can show by explicit construction that each of these exist. So the first figure, tetrahedron, this is just 4 sides. 3 triangles around each vertex. You can see it right here. It's a kind of pyramid-looking object. 3, 4 octahedron, so that's 4 triangles around each vertex. This is kind of like 2 square pyramids on top of each other. Icosahedron, this I believe has the most faces. It's a more concave-looking figure. See it here. It has 5 triangles around each vertex. 4-3, this is just a cube. It has 3 squares around each vertex. And 5-3, the dodecahedron has pentagons as its faces. It has 3 pentagons around each face. And yeah, and this gives us our 5 possible Platonic solids. Thanks for watching. If you like this video, please check out the rest of our videos in our Images in Math playlist. Thank you.